ladies and gentlemen. It's my great pleasure and honor to be a chairman of this session. Today we have very, very special guest, Professor Peter. Let me say one important thing that Professor belongs to our community since 10 years because he's a doctor of honoris causa of our university. Before we start lecture, we will have two speeches, and the first speech, so let me ask the rector of the Poznań University of Technology to give some welcome words for the speech.
Ladies and gentlemen, I'm really honored that Professor Peter Wriggers accepted the invitation which was formally, let me say, prepared by our city of Poznań, and of course due to our university. As Professor Sumerka mentioned, we are really proud that Professor belongs to our community because he let me say, accept our distinguished award, which is named Doctor Honoris Causa of our university. We, of course, cooperate for many years with institution that Professor is representing. Our dream is that we will, let me say, enhance the cooperation and accelerate the cooperation with this, let me say, city, because the city is a partner place for Poznań, of course, and nowadays as a Poznań University, the leader of a European university, also one of the best technical university in Poland. We're going to establish new center, it means Center for Advanced Technology. So today's, during a short meeting, we discussed about further cooperation, not only as a institutional ways, but also, in my opinion, particularly about the leaders, which is very important. My dream is that not only young generation will be, let me say, familiar with the agencies which allow us to be involved in some kind of mobility due to postdoc, due to PhD exchange, and so on. So once again, thank you, Professor, that you belongs to us, and of course, I'm pretty sure that the lecture will inspire all of us. Thank you as well.
So now, ladies and gentlemen, as you probably know, every activity needs to have some organizing, let's say, group. And today this group will be only one professor, Professor Kuchma. He was responsible to organize this lecture. So, Professor, thank you very much. And let me ask you to give some short introduction about our professor, our distinguished professor. So,
thank you very much. Thank you very much. And it is really my great pleasure and honor to shortly introduce Professor Peter Wriggers from the Leibniz Universität Hannover. But as it was mentioned, this public lecture is organized in cooperation with the city of Poznań, and the president of Poznań has prepared a kind of address directed to Professor, our distinguished guest and speaker today, to Professor Wriggers, and we can read. Dear Professor Peter Wriggers, I am extremely pleased, and maybe I will use my glasses, it will be better, because then I will read my thoughts and not the word written by the president. I am extremely pleased and honored that you have accepted the invitation of Poznań University of Technology. The visit of such an eminent expert in the field of engineering and technical sciences is a great privilege for our city. In Poznań, we strongly support the academic society through various initiatives. We encourage academic exchange by providing students, scholars, and researchers with opportunities to meet renowned and distinguished scholars and artists from all over the world. I am deeply thank you that you agreed to deliver an open lecture on your academic interest to our academic community, and I am convinced that this will be highly appreciated by both the academic audience and our citizens. I believe that your visit will contribute to a fruitful cooperation in the future. Yours sincerely, and here follows the signature of President of Poznań, Mr. Jacek Jaśkowiak. I would like to hand this small gift to our guest.
John, give it to me before the lecture.
Yes, but I am assigned the second task. I mean, to introduce our honorable, esteemed guest and speaker. So, Professor Peter Wriggers is well known to our community. Is a world-renowned scientist and civil engineer with outstanding scientific and organizational achievements. But especially in Poland, we know in this society his achievements because they are related to computational mechanics and in mechanics in the general sense. And so, but anyway, let me just briefly review his great achievements, but only the main points. So, university education and degrees he gained at Leibniz University Hanover, where he graduated in 1976 in civil engineering. After 5 years, he obtained his PhD at the same university, and once again, after 5 years, his habilitation. And both PhD and habilitation he prepared under the supervision and guidance of Professor Erwin Stein. And actually, the next professional career is also associated with the University of Hanover. Now it is called Leibniz Universität Hanover, where he has worked from 1981 to 1990 at the university. When at 1990 he received the chair of full professor of mechanics at the Technical University Darmstadt, but he returned to the University of Hanover in 1998, where he received full professorship at 2 faculties. First at the Faculty of Civil Engineering, and then in 2008 moved to the Faculty of Mechanical Engineering, where he is staying up to now. He was director of the Institute for Continuous Mechanics, but during that time he also gained knowledge and how I should say, conducted research abroad. And in 1983 till 1984 he visited University of California in Berkeley, where under the guidance of Professor Robert Taylor and together with Professor Michał Kleiber, as it was mentioned, he stayed there, and he visited then this university many more times. Yes, so, and he was also from 2005 to 2009 conjunct professor at the University of Newcastle in Australia. And Professor Wriggers has held many positions in science societies, panels, and boards. Let me just mention that he was vice president for research at the Leibniz University from 2015 to 2021, and also vice president of International Association for Computational Mechanics for Africa and Europe, president of German Association for Computational Mechanics, president or vice president of GAM, the German Association for Applied Mechanics and Mathematics, and many others. And Now I just like to mention areas of research. They are mainly concerned with the computational mechanics and developing new tools, new methods. And what is characteristic for Professor Wriggers' research, he all the time takes the challenging problems, and actually his research is at the front of knowledge and to expand and to get new insights, but using modern computational tools. And he's the co-author of 14 books, especially in the nonlinear finite element methods, which is cited many, well, I think that 3,000 or even more times, and over 630 articles. We have already talked with Mr. Rector today about some bibliographical indicators and people who did a lot, who gained many very interesting and new results, don't care about that. But anyway, let me just quote the numbers which I found yesterday. I mean, H index is 82, and number of citation over 32,000. Professor Wriggers is organizer of 22 conferences and congresses, and editor-in-chief of computational mechanics and computational particle mechanics, being also a member of many journal boards. And for all these achievements, great achievements, and for showing new directions of research, he has obtained many prizes and awards. And I just like to mention, I mean, his PhD thesis was already awarded, and he received 3 prizes from the International Association for Computational Mechanics, Euler Medal, and Grand Prize of the Japan Society for Computational Engineering and Sciences, and also Zienkiewicz Medal from the Polish Society for Computational Mechanics. And as it was mentioned, he obtained also 3 doctorates. The one very important for us from the Poznan University of Technology in 2013, and also in this year the honorary Doctor Honoris Causa from the École Normale Supérieure Cachan in Paris, and also from the Darmstadt Technical University in Germany. And as I said before, Professor Wriggers has also supported development of computational mechanics and mechanics in general in Poland, and has participated and initiated many endeavors, I would say, for Polish scientists. And together with Professor Wodegowski, we had the privilege to stay at the institute in Hanover, the Institute for Construction Mechanics, and then Institute for Structural Mechanics and Numerical Mechanics. And I just like, and Przemek Litewka also, yes, that's right, yes. And I just like to mention that because I attended strong team. I attended many lectures, and I just like to say that at the conferences where Professor Wriggers presented his invited or plenary lectures, and the number of them is over 50. We were waiting for the lecture because we were sure that new elements, new ideas will be presented. And so wir sind gespannt, and we are looking forward for the lecture today. Professor Wriggers, the floor is yours.
Thank you very much for these very kind words, almost too much. I have to say that I am very happy to be here. I like to come to Poland. I was last year in Swinovsky. I hope I pronounce it halfway correctly. In Germany, it's Swinemünde, right? And because you had this conference there, so we had a nice time, and could see what Polish colleagues were doing, and I also could give a small talk there. so I hope to be back anyway. You might be a little bit disappointed today because I thought it was a public lecture, so I have no questions in my lecture. Sorry about that. But I would like to show you a little bit what we are doing well, what anyway the role of numerical simulations in engineering and applied sciences is. And I think it will become more and more sort of pronounced actually, because the tools which we have are also getting a lot better. So this is basically it. And if we want to start, I always like to start from the history. Again, thinking of a public lecture. This is something very old, the Pantheon in Rome. It's still without cracks visible. The problem is that it's sort of a complex building, and it was designed by the Romans without any computations. So I don't know how they did it actually, because it even has different types of concrete here. If you don't do that, then you cannot have a cupola which is like a sphere, because it has to look a little bit different. So this is a very, very, let me say, unusual design, which was sort of, which is in place nowadays. And if you go there, it's really amazing how this building looks. Then it started to get on, and if you look at these kind of things, which is, I think, something we even nowadays can see, which is good. It's about a civil engineer. Vitruvius was one of the architects in Rome who wrote books about engineering. And he said, a builder who neglects scientific education, strives only for workmanship, will not reach appropriate mastership. So that's the first thing, right? Even the Romans knew that. On the other hand, builders who only rely on calculation and scientific education seem to follow a shadow, but not a real task. So that means this is what we have to do in engineering. We have to combine theory, we have to combine computational work, and what he says here, builder, however, who combine both scientific education and workmanship will reach their goal faster and more successful. I think this is very old. It was some years before Christie, and it still holds, right? So from the engineering education point of view. A shorter version, I mean, I'm from Hanover, Leibniz, he said Theoria cum praxis. This is sort of the same thing, and it's having 3 words, right? A little bit more pronounced. Okay, so now just an idea how long it takes to get a good theory. If you take this beam, and people were interested of sort of doing the computation of beams sometime and to understand what was going on, then you can follow Galilei. He tried to do a first model, and he assumed that this beam will rotate around this point B, and then he sort of did some calculation with equilibrium. He came up with this sort of set of forces. And as we know, this is not correct because there is no horizontal force if you push a beam down. So this means the model didn't work. Next came Leibniz, who had the same idea. He also had a point where it rotated around, but then his idea was to have basically here a distribution of the forces which looks like this. Still, there is a horizontal force. And then Mariotte came and then solved the problem by putting the rotation axis in the center line, and then everything was working. But you see here, 50 years. 50 years of the most clever people at that time to get it right. So this means it's not so easy to come up with good models. And this is something which one always has to have in mind if one thinks about things beyond the good. These kind of things could be, of course, used then furthermore for designing first steel bridges. Here's a little bit funny cartoon of these 2 guys who are the pillars and sort of support this guy here. Then the other one was the chain models, which people used. Basically, the idea is that the chain has only tension forces, and if you take it around on the other side, put it upside down, then you have only compression forces. this is very, very basically necessary if you basically want to design this sort of stones which only can sort of sustained compression some buildings. And this was then used as a design criteria. But in the meantime, there came also people like Jacob Bernoulli, construction of the elastic line. You see this drawing. It's not so easy for a normal builder to understand what is going on there. So I think people relied more on this kind of approach than on this mathematical approach here from this point of view. So this was way ahead of the time. Then came the Peters dome, and this is a classical engineering problem where they made some mistakes, and due to the sort of wrong way of setting up the cupola, they had these cracks here, and they had to be somehow healed. This was the first thing where really a mathematical model entered the, let me say, scene, and where it was used to somehow save the construction. Actually, they also did a chain model there at that time. This was Giovanni Pollini who solved this problem. Then you have a very famous guy named Gaudi. You see the Sagrada Familia. I think it's almost now finished. Took some years. And how did he design this kind of thing? He also used a chain model. And this looks like that. So every little sort of, and you have to be very precise, it's sort of also an optimization problem, because you put here all these little weights on there to get the real shape, which is hard to see. There are some chains underneath so that you basically could get the shape. So this was sort of state of the art around the end of last century before, I mean, like in 1900 from this point of view. So then, of course, we can go into the history of mechanics, how this whole thing built up. We have, of course, Newton, classics. Then we have Euler, who went into hydrodynamics. Then we have Cauchy, who basically started with the theory of elasticity, which is somehow a theoretical background for all solid mechanics and all structural analysis. Then for the fluids, we have Navier and Stokes. We have Kirchhoff, who was a guy who developed the plate theory. It's a correct plate theory. The development was done before, but it was not quite correct. Then we have the shell theory. And then it started to have plasticity theory and so on. And these are bases, which we show here, which are still used as theoretical models for engineering. We are not much beyond this. Of course, we are doing sometimes something different, looking at microstructures and so on, but the basic stuff is basically here. And interesting enough, these first things were basically like particle mechanics, and then from there on, these particles were sort of combined to a continuum, and these theories are all based on continuum mechanics. Now, of course, my talk is about numerical simulations. So far, there were no numerical simulations. Sorry about that, but somehow we have to start. Of course, coming from the Leibniz University, I start with the first calculator for Spacious machine, which Leibniz developed. Was not really completely working. I mean, the principle, this Professor Stein, my former advisor, has actually shown in a DFG project that the principle of Leibniz is completely correct and works. But at that time, they were not precise enough in manufacturing the teeth and for this, I mean, the mechanical work, the real mechanical work was not good enough at that stage. Then there was another machine, Babbage, where it was an analytical engine, and then came sort of the computer. Most of you know the ENIAC, maybe some of you also know the Zuse. He was actually a civil engineer. and said this structural analysis stuff, you have to solve big equations. This is not good for doing it by hand. You have to do it automatically. So he moved from civil engineer to this thing to basically find out that this is good. I once heard a talk by him, it's a long time ago, but very nice, interesting guy. And it looks really, if you compare this to the American system, it looks somehow better designed, right? Looks really for me. And the stuff, I think, was way ahead. Of course, there were no transistors. These were sort of relays which had to click, so on and out. So you couldn't do big things with this machine, but you could do something. Then, of course, when I studied, this was my pocket calculator. Then when I still studied, this one came out. I don't know, some of you might know this, the HP 35. I could not afford it. It was so expensive. It was about, nowadays would be like at least 700 euros. And at that time it was a lot of money. So this was out of reach. But it could do sine, cosine, and all these kind of things, and very precise. Now we have the iPhone. And probably most of you don't use the iPhone for computations. Or does anybody use iPhone for computations?
Pocket calculator, yes. Pocket calculator, yeah.
No, I mean this kind of thing.
No.
Not yet.
You can, you can download that, QuickFem. It's sort of an app. And there are other apps, if you are interested, I have a sort of a bunch of them. You can, and the thing is, if you then do the computation, these are 5,800 unknowns here, finite element thing, and it solves it in 0.7 seconds. So this one is really useful now. The only thing is it's not so handy. I mean, nowadays we have basically computing power, which when I was young was sort of one room of computer, right, which is now in your pocket somehow. So this is the development of all these kind of things, and I think it makes sense. So historically, numerical method also, of course, need some historical background, because I mean the old formulations of mechanics were, of course, done in a way that we wanted to solve everything analytically. And now, I mean, we have Ritz, variational method, Galerkin, some others. The first one who really started finite elements is Kurat, a mathematician. Probably pretty unknown, because this is Turner Clough, Fem in structural mechanics. In Berkeley, they started to develop it also together with a company, like in Boeing was also done some development. Or Gyrus energy method and finite elements in Stuttgart. But these were not really finite elements, energy method, but this was the way to go. But actually, if you read this paper here, it reads like a very modern way of doing finite elements. So this one is good. And what he did, he solved the problem in his, actually in an appendix. So it was like a little exercise. Okay, let's see whether it works or not. So, and he not only solved the problem, but he also did already a convergence analysis. So this is quite nice. Of course, the problem was simple, and he probably didn't have a computer, so he sort of do symmetry things and so on. But this was the beginning. Since then, of course, if you look at the sort of finite element development, theory of elasticity, 65, theory of plasticity, 70s, contact mechanics, 80s, finite deformation. So from then on, you could really use it to solve problems like this one, crash problem in this case. But one also has a different view. If you look at particles, then you have molecular dynamics, physics. You can basically see that. Actually, there is Nobel Prize, which was won actually for numerical simulations of some DNA structures in that way. And then there are also discrete elements, which basically where you treat each of the particles, which are like sand particles, as one little element, which is independent from each other, and then they come in contact together, and you can solve quite big systems in that thing. The thing which is a quote from also Wriggers is basically the computer shapes the zero. That means that we solve problems in a way that can bring it on the computer. And classically, the better the computer is, the more refined the theory can be. Right? So this is a very simple thing. Now, okay, now let's go to modeling. This is also a classic. If you do modeling in solid mechanics, you have a TV tower. You can model this as a three-dimensional object, which it surely is. You can model this as a two-dimensional object. If you want to have some buckling phenomena, you can say this is a sort of a shell, because the tower has an inside and is there. Or you just say it's a beam. It's long, so it's a beam, and if you really want to be very simplistic, then you say, okay, this beam has a certain spring, this spring system and a mass will also provide a model for this tower here. Of course, now the question is, as an engineer, which one do you need to take to solve your problem, right? I mean, so this is something you have to be aware of. This is, of course, more costly, and this one doesn't cost anything. So from this point of view, you have to think about it. And usually what people do, they use first simple models to do design studies to somehow optimize it, and then the final design will be modeled maybe more complicated. And these are, of course, areas where we can apply this. Some mechanical problems in solids and fluids, electromagnetic problems, biomechanics, and so on. So all these kind of things can, of course, nowadays be solved. You have standard software around which basically can be applied. The thing is, in engineering, what we want to do is we want to do a prediction of problems on structures which have not been built and which you cannot build like a car as a test object and then see how it performs. And then if it doesn't perform, you build a new one. I just put here sort of a prospective bridge on the street of Messina, which is 3 kilometers long. So, I mean, there is no way to do a testing on this bridge in whole. So you have to do you have to have some possibilities to numerically predict the behavior. And this is quite complex because you have wind forces, you have forces from the car, you might have some earthquake, whatever comes around. And as an engineer, you have to design it. And it should stay there at least for 50 years, right? Golden Gate Bridge, and so on. So this is the kind of thing where we need real scale experiments are not possible. Small scale can be possible, but then you have always a problem whether you can transport from your experiment really or predict into the future. So the only thing which you can do is numerical simulation, and this has to be reliable. Engineers, civil engineers are known to do that, and they were actually also the first ones who developed these techniques because they had the speed to do that. And if you now see all these fancy high-rise buildings which are twisted and whatever, nobody could have built them 50 years ago because you could not compute the forces and the stresses. But now with the modern numerical tools, we can do that. So what is a model? That's a projection of the reality onto a set of mathematical equations. So this is what I tried to show very early in the beginning. You have the beam, and then you have to find the right equations for the beam. I didn't show the equations, but at least you have the right stuff. Or onto a set of experiments. This is classically not my sort of talk. So if you want to do predictions, so then we have one thing, for example, car crash. This took 20 years to get it into the industry use. because people had to rely on these kind of things, and before that, everybody did experiments, which are actually extremely costly, because a car which was not built before cost 1 million euros to sort of do it by hand, right? Or 500,000, whatever, but it's very expensive. So this is the first thing, prediction on the bridge. Then we can try to use this kind of thing to explain some physical phenomena which can happen. For example, if you have here, this is a mortar from concrete. Okay. Back to civil engineering. This is how it looks like if you do a real scan. And this is a prediction of the sort of setup of the constituents by chemistry to find out whether you can get the right predictions and to understand the processes of, for example, the development of the mortar over time. And of course, you can also use some decision-making models where you basically help people to make decisions in the political way, and this can be based on, of course, also on physical laws. Now, if we construct a model, what do we have? We have a real-world problem, we have a mathematical model, then we have some data which are given to us. Then, of course, we solve this model equation, which is our mathematical model. It can be complex, can be simple, can be complex. We get results. And then we always have to think about it. Is this correct? Is this not correct? What can we do? And if the results we don't like the results, then we have to go back and eventually change our mathematical model. So we have sort of a circle. The thing is, it's often not easy to get the data. Geometry is relatively easy. Loads can be more complicated, and then we have some boundary conditions which are also quite complicated. There's a lot of stress about climate models because people don't know really the initial data, right? So it's not so easy to predict the future if you don't have these data correctly. And it's very hard to get them. And of course, you also have some randomness in there. So material has a random distribution. If you look into the details, the loads can be randomly distributed and so on, which classically one has to take into account. And what we want to look at here from the solution point of view, of course, is a numerical solution, which classically, if you take finite elements, is in a way an approximation. It's not the analytical solution of the mathematical equation. But there should be something. The models are very complex. For example, nowadays, if you do a crash analysis, you put inside the car also the people. And the people have even shoes on and wear a tie and whatever, right? But and they are basically made like real men with bones and with everything. So you have a complex model which you put into this car to understand what the acceleration of the head is, things like that, to really design the car in such a way that people are protected. And we have. This is very nice to have, but there is a constraint from the engineering practice. The constraint classically is, if you go to industry, the result has to be there the next day. In the university, we can wait 3 weeks, right? But in industry, you don't want to wait for 3 weeks. So one has to think about new methods, and this is some research which is, of course, in many places going on. Faster computations, using GPUs, using neural networks, using whatever kind of models to enhance these computations. Just for the fun of it, here is some example, which is actually not really engineering practice. This is a mixer, which we somehow, one of my postdocs investigated here in this case, where we throw a lot of particles inside, and then we have 5 million of particles. I mean, you can even have more, but you want to solve this. Each of the particles can come into contact with each other. They can change their position, everything. And you can only solve this on supercomputers in the moment on parallel situations. You can also do it on GPU systems, but at that moment we did it on parallel computers. And if you do that, then we had here almost 3,000 number of cores. That means parts of this thing were basically, so this is one part which goes in one processor, and this is another part which goes into another processor. So you basically subdivide your system in different pieces and get these different domains. And then you want to solve this thing. And here is sort of somehow the solution. It looks very nice. I mean, particle methods always look nice because you get nice movies. So, but this is sort of the problem which we have here. So it's basically, and what you can see here is sort of now also the development of these domains, because if the particles, due to the mixing, come into contact with other particles, we have to change the domains. Oops. So let me just see. I think I have to push it here if I can. Okay. Well, if you look at that, you can see here sometimes that the domains basically change in a way when the plate comes out. And this, of course, means that the efficiency of your code is not as you want to have it. Like this would be the ideal efficiency. So if you have 3,000 processors, you will have a factor of 300 because we sort of had sort of a basis of 12 processors in the problem. So if you multiply this and also get 3,300, but we only get 100,000. So this is not good, right? Then, of course, as an engineer, you have to work on it, and then you can find better ways of redistribution of your model, and you get this kind of behavior. Now, that means we have more advanced theoretical concept, advanced numerical techniques, advanced computers. I said already, result has to be available in the next day, and the idea is to use reduced Euler models which can be found in that way. And they have to be available for nonlinear systems. So this is not easy. I mean, these kind of models are well known for linear analysis, but not for linear analysis. And it would be nice to have some toolbox which does it, like the phone, where you can basically say, okay, to my phone I want this, and it solves the problem for you. Now let me go to some examples. I think this is interesting. One is, if you look into materials, classically a material, wherever it's coming from biology, from food products, ice cream, this is a piece of ice cream here, composite material, cement, ice is turned around, sorry about that. Cement paste, alloys, so we have composite materials, a lot of materials in this way. And the thing is, sometimes you know that you have this microstructure, but you want to have the general behavior of the material for your predictions. So that means that we have to somehow project or predict from the microstructure the material behavior of the materials which we have at hand. This is one example, is cement paste. You can see the cement paste has different constituents. I don't want to go into the details, and it has holes inside. This is a CT scan. You can go to granular material, it's clear. If you want to model sand, you will never model all the particles. You will model them in a sort of a continuous way and have that. If you have some materials like aluminium boron alloys, they look like this, and sometimes you want to add this. You have woven fabrics, composite materials, you have materials which have complex contact surfaces and so on. And what is clear is the material parameters of these single phases here, the red and the orange ones, influence, of course, the global properties of your material. So it's very interesting to understand what is going on. And then the other thing is that these phases are basically randomly distributed. So I mean, if you take this one, you can do some computation, but it's not clear whether it really will sort of give you all the results you need. So you have to do some statistical computations eventually. And I just want to show you some idea about this, about two ideas. I will come back to this one in a moment. But before, I just wanted to look at, for example, forming of thin shields in metal. You have polycrystalline microstructures with different sort of orientations of the crystal. And what we want from this microstructure, we want some material law for the sheet metal here, because this is sort of on a micrometer level, and this is of course on the centimeter level. We want to have for the engineer some material law which is coming from here. So we can do something like a homogenization process, obtain the results here and put it inside a material law which governs this. And in order to obtain these homogenized values, what you have to do is you have to, for example, do a shear test, the micro shear test on these polycrystals, and then you can see that you get a nonlinear behavior. And if you can basically then use it for homogenization, you can use it in your real application. And the other one is, of course, concrete. Concrete is also something which everybody knows, and we will use it for a long time because there will be building built. But if you look at that, then if you take something out, then on the centimeter level we have something like gravel, and here's this blue stuff is a mortar, and so on. So we have the construction, which is meter level, this is centimeter level. But if you look then in detail here for the mortar, you get this one. Now we are at the micrometer, and you can even go to the nanometer, and all this stuff sort of governs somehow the behavior of here. So it's very complicated. And we talked about this today. If you want to have some ductility, you have to think about where you have to add things, and to find out how you can basically enhance or these materials in some way. So we have actually done some computations on that. So we got this three-dimensional geometry, which was based out of a CT scan some time ago, and the spatial resolution was 1 micrometer. It's already some time ago that we did that. I mean, nowadays you can have a better resolution. But the idea was to represent this microstructure by finite elements. I mean, do a numerical simulation. We know the basically different material properties of the material here in this case, which are all different. So we have unhydrated film, we have hydration products, we have pores in there. And these computations, if you look at this, and 800,000 degrees of freedom, which you can, at that time you could solve in 5 minutes. Now probably you can solve it in 1 minute or less. But the thing was that we needed to do, because of the randomness of this microstructure, we needed to do some computations. In total we have used 9,200 of these, which you can do in parallel. I mean, just this is very simple. You just use 9,200 computers, then you have it in 1 minute, or you use. So this is not a big deal. But if you do it, then with this, which is something like, then you see a Monte Carlo approach, and you see that you get basically a Gaussian distribution here for the material probability density of the here effective modulus of elasticity. Now the crunch is you will get the same like in experiments. So experiments are usually done not on this micro level, but done on the sort of next higher level. And the colleagues from Institute of Material Science at the RWTH Aachen, they did a test, and you can see here that we got our numerical results are very almost too good, right, in this direction. So we got very nice results. And interesting enough, we also tried it in 2D, which of course would be a lot faster. But then you are losing sort of the three-dimensional effects, which are inherent in the microstructure, and so then you get wrong results. So the message to learn is, if you look down in the homogenization, anybody does 2D, in this case, you can say, okay, I don't believe. I mean, you can do it to test your methods. That's what people often do, but you cannot do it for a real prediction. As I said, this is civil engineering. You can have these are classical programs which you can get everywhere. This is sort of something I wanted just to show. I don't know whether you know that thing. It's sort of a nice thing. A colleague of mine, Professor Schweizerhoff, he was very much involved in this company Dynamo, which distributed this crash code in Germany. And then there was sort of from the German Auto Society, and the CT is sort of a German journal on computational computer science. They were doing a sort of challenge, saying, okay, can we do a computation of the crash of Lego cars, which is almost as good as the real test. So they bought, again, these are two Lego cars, right? A Porsche and a Bugatti. This is what you take. And they were really run as a crash on this ADAC, I mean, from this auto club, on their normal testing facilities. And let's see whether I get it right here. Yeah, I think this is correct. Yes. Now you can see the real testing and the computation. You can even see that this tire here has the right behavior. This model is not easy because they model each of the Lego pieces. And then you have to find out how the friction between the Lego pieces is to do that. So they even did some testing on this thing, but they tested some Lego pieces together and then they assembled them and got the result, which is quite good from this point of view. So this means that prediction of this kind of car crash is even possible for these toy programs. But I always liked it because it's sort of a nice thing. If you look at this thing and you put in Lego bed in the internet, you will find it, and you can download even more movies and so on. Here you can see that, I mean, all the parts are flying away like rigid bodies. And here's again the real computation, the real test and the computation, which looks quite okay from this point of view. So this is what numerical simulations can do nowadays in specific areas. And this is a commercial program, Palestina, which now I think it was bought by ANSYS right now. So it's now in ANSYS. Another prediction which we did in a process is, of course, is like environmental thing. We had a study area which was the River Elbe. It was a European project which we did together with some people from Italy and Spain. And the question was, here you can see the picture from the river. Here is sort of a model of the elevation inside this part. And the thing was, if we have something which is spilled from a factory, a contaminant thing, so how is it distributed in this area if we have high water flooding? And so basically this was the water depth in the river which we got, and here you can see the distribution of the pollutant during the flooding, which almost looks like the same, but then you can watch that here out of a sudden you get an area where you have sort of a very high concentration because there is sort of a slack water thing. So this is numerical models. You can actually then predict things which are valuable for say, political designers, for people from the park, this is then for this is World Heritage Area. It was the former border between East Germany and West Germany, and so this was why nobody touched it, right? So this is why it is now a World Cultural Heritage from this point of view. Another thing which we do is, or which we did, is somehow blood flow simulation, patient-specific aorta. FSI means fluid structure interaction, so the aorta is sort of moving and blood flow is going. Now, the thing is, classically, if you have a patient, you can get this MRA image. Then you can basically, then a model process starts. You do something like you compute the center lines from this image, and you can do a segmentation where you find out how the thickness of the aorta is. Then you can, and here you can sort of relate the thickness of the aorta to all this construction, and from there you can basically then do a solid generation, and you get sort of this aorta which sits here, the model which sits here in a way in the patient. So this, of course, have to be embedded in the body. So you need actually for your model some springs to do that, and then of course you also need some boundary conditions and inflow conditions for the aorta and things like this. A postdoc of mine did this because we were working together with a surgeon from the medical school, and here you can hopefully see this is basically for the heartbeat, for how it pumps, right? Sort of a slow motion of a heartbeat. It's very hard to see the deformation, but there is deformation actually. Otherwise, you don't get the computation right. So you have to include that, but it's in real. It's not so easy to see. So this is something you can also do with numerical techniques, and we can help medical people to predict things. So if they do something, some surgery, some bypass or whatever, they can predict beforehand what will going on. And then this is some area which we are currently working at, to go into more other things is tissue mechanics. And the idea is we want to look at the sort of way how the development of an arteriosclerosis, which basically is in many cases, many people have that, is taking place. And there are actually two theories. One is a classical one from cardiology, that from the inside of the blood flow there basically happens something, and then you have, then these sort of inflammation starts. The other thing is, if you look from the outside, and I will look at the outside theory, which we will describe a little bit more in detail. But the thing is, if you want to look at tissue like this, it's very complex, because you can see what's going on. There are different pieces and little smart muscle cells, there's collagen, there's all sorts of things in there. And in the end, we have something like we have a multi-scale problem. We have molecules, we have some collagen, we have some other parts. Here's collagen fiber. We have here the sort of the tissue wall. So this is quite complex. I don't want to go to there in the detail, but just talk about the little model which we have. Does it work? Yes. So basically, this is sort of the other theory for the development of plaques and arteriosclerosis, which basically happens somehow, and then basically you will have some part here which somehow makes the blood flow, or sort of reduces the area of the lumen, and by that basically you have higher pressure, and eventually you can also have a clot. So this model here is the following. This is done by my colleague Axel Haberich from the medical school. He is actually a surgeon, and not. And he has done so many surgeries that he always saw that there are points when never arteriosclerosis happens or occurs, and others where it occurs. And his idea, it comes from here, from the vasa vasorum. The bigger arteries have sort of small blood vessels which basically transport some nutrient inside the blood vessel to basically come up with this. And there's no computation, so this is just, he gave me these movies, so this is, but you can see, I mean, when people grow, actually this was sort of a young man, young woman, this sort of this vasa vasorum is larger. Now you have this is if everything is okay, but what and this is actually quite interesting. This is a very new picture where they actually look at the blood flow. Here is the lumen, and here is basically the inside of the artery. And you can see the blood here. This is from the vasa vasorum. If you look at this, you can really see how this sort of happens here. This is some new experimental technique. And so what his idea is basically that at a certain stage, somehow some bad guys come in here, some bacteria from the outside, either through fine dust, avoid fine dust. So this is not good. He told me that if they have fine dust in Beijing, that the surgeons sharpen their knives, because then they have 3 times the number of problems than they had before. So this is something. And what happens is these bacteria start to basically clot here some of these parts, and due to this, other guys move in. Due to this, basically what happens, there is no nutrition anymore, and then basically what starts is here sort of the formation of the plaque, and then the sort of change of the cross-section of the lumen, so that basically the blood flow changes. And this is of course a disease. So the theory comes from the outside and goes then in the inside. The other theory, it comes from the inside and goes sort of in the vessel. Maybe both is right. That's my feeling as an engineer. But he asked us whether we could model that, so that his theory is sort of supported by our numerical model. So what we did, we started to do that, and the general idea was that we have this occlusion here at some stage, that then there's a nutrition scarcity. This yields an inflammation, and then due to the inflammation you have the plaque forms. And this is basically how the whole thing works. And the only problem is, if you make a little bit more complex model, that we have so many different species which we have to take into account. So this model actually is not only mechanical, it is also chemical and biological. So we have to solve, besides the mechanical equations. I promise that I don't have equations here, but I can send you the papers if you want, anybody can get it. We have also some transport equations we have to solve in this case. So the idea is, if you have an obstruction in the Newton scarcity, then monocytes develop, they can die, or they can change, they can migrate to macrophages, they can also contribute to the plaque. The macrophages can contribute to the plaque, they can also go into, develop into foam cells, these can be attracted, and we have smooth muscle cells, and all this kind of stuff enters the plaque and stays there and sort of enhances the soil. So first of all, we had to somehow develop a way to generate the vasa vasorum network, which we have done somehow to compute this thing. Then we have to set up some Newton scarcity and eventually some monocytes which are sitting there, and then we can develop or see how this whole thing develops. So we can see the nutrients. This is sort of are less in this case. There are foam cells developing, the monocytes, macrophages, collagen, smooth muscle cells, and the whole thing sort of gives us sort of a system or a problem which it uses here the cross section, which is the arteriosclerosis after 12 months. So this can be predicted by the model. Can of course challenge everything. We try to get all the parameters from the literature which we could get, so I think it's quite okay. But this is how it works, and we have some papers. If anybody is interested in reading them, I can send them. So this is what the plug looks like after 10 months in this direction. So on this, to close, is that okay or not? Fluid particle flow, it's also something which we always have in nature. It's biofilm growth, it's this kind of transport, it's sort of dust which is thrown in the air. There are mixing problems. There is some technical problems where you basically suck some stuff into boats. Here's a mixer, and a lot of different mixing techniques, and all involve a fluid and some particles which are sitting inside. Chemical engineering is also something like that. And we wanted to solve that. So we tried to do this. And for this we had these particles. We thought, okay, the particles are quasi-rigid spheres. They have different contact forces, how they interact. They can also adhere. There's gravitation. So this is one part. And then we of course have also the fluid, which can be solved by classical fluid methods in this way. And then we have to couple all these things. I don't go into the details how we do the coupling, but there are different methods, and we did a full coupling of the, so that all the fluid forces are acting on the particles in this case. So for example, here we have particles which have different densities. Some go down, some go up, and if you run this picture, you can see that they lighter particles move in the top, and this other ones go to the bottom. This is something which you can solve there. The next one, let's see. Do you see that the flow field is quite turbulent here, so which we of course resolve. So I mean, from the point of view, if you want to know numbers, these are like 20 million Finite elements of the flow field. You can do the same, but you can say, okay, we have a density like this that and adherence between the forces, so that some of the particles will be lifted up by other particles, so that we basically have something where these particles which want to fall down, they adhere to the particles which are lighter and they move them up. So we have a different sort of mixing process. Or we can do real mixing, where you blow something inside a set of particles, and you get this mixture, and you can see whether everything is mixed fine or not. So this is another possibility which you can do in this case. As I say, and here it was a funny thing actually given to me by Professor Owen, late Professor Owen from Swansea, England. They had this kind of problem where they have some gravel here, and they want to suck the gravel up like a big vacuum cleaner from the ground. The point is why they wanted to do it. It was some people in South Africa, because they thought that there might be gold inside that kind of particles. Right? So we also try to solve this, and you can see that it's possible to suck this gravel from the ground into this pipeline or pipe which is up there. So that was some problem. Another one is, which also often you have in biomechanics, is that you have some scaffold, and you are interested on what is sort of adhering to the scaffold. You have a motion of particles, so you can see sort of here the flow field, and here you can see how the particles adhere to the scaffold. And then, but then the shear force is so high that these particles are again sort of lifted away from this scaffold, which is easily seen. This one has something to do with also the arteriosclerosis. Think about this, that this is sort of a reduction of the arteries of your sort of cross area in your blood vessel. Then, of course, you can look at the sort of red blood cells, and they can also sort of clump together and build a thrombosis. Right? So this is nothing which you want to have. Something like this can also be modeled with these type of techniques here. And this is what can happen then in this case in the end. But for this, I mean, you see also that there's out of a sudden it's a laminar flow, and out of a sudden there's a quite turbulent flow, which ends up to this kind of thing. And this is one of the last pictures which I have. This was something where we were looking at biofilm growth. So these are little species in the biofilm, and sort of you see these go here, and then they can adhere at this ground, and this is a certain actually experimental equipment where you have basically an outlet here, a circle, and this higher cross-section sort of reduces the flow velocity, and due to that the biofilm, the particles sort of adhere to the ground. They don't adhere here, but they adhere here at this stage. So this was something which we did together with our dental clinics. They are very interested in biofilms, in implants. Okay, now I come to the end of my talk. We have seen that numerical simulations, I think, are a little bit across disciplines. Mechanics, of course, is an old part of physics, but in a modern multidisciplinary phase, it's still alive and makes a lot of sense to look at it. You can solve a lot of problems, of course, and what you can see is that computation mechanics, which is sort of behind these numerical methods, and this is a term which is used nowadays everywhere, is basically a mixture of continuum mechanics, applied mathematics, because otherwise you don't know how to solve equations, you are in bad shape, computer science for all the graphics, whatever, and of course also modeling techniques. And never forget about the models. They are very essential, especially if you want to do something new. Now, this often is also multidisciplinary. We have seen some results which we have done with people from geotechnics, people from material science, people from medical engineering. So, I mean, this is sort of a multidisciplinary area. And from this point of view, very good for research, because there are a lot of problems there. And as I said, the problems can be highly complex. We have often numerical and algorithmic challenges, which I didn't talk about at all. But everything looks very nice and easy, but sometimes it's not that easy. And we have some problems. Everybody who has done something like this knows that. Of course, you have different modeling scales, from the micrometer to the millimeter to the meter or to the kilometer, depending on where we are. And as I said, 3D simulations are often a must to predict real engineering problems. Now, of course, what we want is reduce experiments, eventually also animal testing in medical sort of application is a big thing to do. And from this point of view, help in patient-specific decisions. Fast implementation of modern hardware. I showed you my phone on the pad. This could be a very valuable tool for like physicians if they just can use an iPhone and say, okay, this is sort of the thing, and I change a little bit and press a button, get some results, and then our methods will be used more and more also by other people. And of course, the new value KI-driven approaches, artificial intelligence, I took the German name, it should be AI, approximations for fast predictions. The problem is with AI, if you just take neural network, stuff like this, be very careful because prediction is not possible. You only can compute within the range where you have the data. If you go out of the range of the data, forget it. So there you need a little bit more physics. But this is my last sort of word of care. So thank you very much for your attention.
So thank you very much, Professor. I don't know how in Germany, but sometimes in Poland we used to say that 13th of every month, the day of the 13th day is unlucky, but I'm sure that today we can say that we are more than lucky. Starting from the very beginning of this day, we have a beautiful gold period, and now we have brilliant lecture. So, Professor, lecture is open for discussion.
Just one word. In Germany, it's only Friday, number 13. So I'm on the lucky side.
Some questions. So maybe I could start. You didn't mention about quantum computing. So do you think that it is the future of computational mechanics or not necessarily?
Well, it's complicated. I think you never should say no. At the moment, I think quantum computing is very, very well, sort of a very good tool for like people in the Secret Service, where you want to compute numbers which nobody can guess, right? But from the point of view of solving real equations, I haven't seen anything at the moment. But that doesn't mean that it doesn't work, right? Because somebody have to come along with a good idea, maybe some different way of solving equations. We know that there are a lot of different ways of solving equations. Right? You can even solve a dynamical problem to solve a linear equation. So I mean, there might be some ideas which can come up and which one can pursue. At the moment, right now, I think it's the future kind of thing.
Next question. Professor Kushman.
Well,
You always
No.
have medical, at least quick.
I just like
three
to ask about this quota is because how do you understand in the positive sense that we should be reliable and aware of some dangerous directions of study on research?
No, I
or
was more in the positive sense.
The positive, yes.
But I mean, this is something which is still not finalized, right? I mean, if I give you any microstructure of a material, it's not so easy to reduce the testing on these predictions. Right?
I ask because this künstliche Intelligenz, artificial intelligence, this for me.
But it's a fashion at the moment, right?
Yes. Yes.
The question is whether it's really a good fashion. I mean, that's not clear. I mean, it's used in many cases, and there's for sure a lot of applications, right? For example, I had to go for the 70th birthday of Professor Onyate this year to Barcelona and had to prepare a general lecture. And I said, what can I do for him to have a nice, sort of say some nice words about him? And then I asked ChatGPT to do a poem for me. It took ChatGPT exactly 5 seconds to come up with a nice poem. And the English guys were saying, how did he do it, right?
Yes, that's right.
And I actually told them that it was ChatGPT, but
Okay.
it was, I mean, I just want to say, I mean, there are a lot of things where artificial intelligence can help us. The question is whether it can help us with modeling. At the moment, I mean, I tried several things. I mean, if you say something to, for example, ChatGPT, gives me a short account about arteriosclerosis. It comes up with 2 pages, which are quite nice. But if you say, give me the equation for the Timoshenko beam, then comes something which is wrong.
Yes.
But the student might not know it, because
Yes,
it's
that's
almost
the problem.
right.
Yes, that's the problem. Thank you very much.
Yeah.
Thank you. Next question.
Okay, thank you. Thank you very much, Peter, for this inspiring lecture. My question is also devoted to artificial intelligence. Do you see any possibilities, because we have very strong, powerful computational tools. We can generate millions of different situations. Do you think it would be possible to use a method of artificial intelligence to predict, for instance, something in biomechanics, in the behavior of the people? Maybe to say then that, well, you have to do something else because you're already close to heart attack or whatever.
Yeah, it's hard to say, but by my feeling is, I mean, there are of course different methodologies in artificial intelligence, right? I mean, the classical neural networks and the physical informed neural networks and so on. It's all under development at the moment, right? So there's not really the approach which we can use, and so from this point of view, of course, it's worthwhile to look at it. I mean, I'm not saying that it's that I don't want to see it. I see, for example, one area which is like if you do multi-scale computations, you know, finite element square, where you have sort of you want to sort of look at the microstructure at a certain level, but want to include this in your general system. If you do this including of the microstructure with artificial intelligence, with a neural network or PIN, then of course this is very fast, and so you can then out of a sudden use these kind of multi-scale methodologies within your normal, I mean, I've not done it, but this is my feeling, within your normal simulations. So if it comes to the medical part, I think then one has to think about these physical informed networks, and I think there is possibilities to do that. I mean, one thing, of course, the medical people, I mean, if it goes to the classical thing, like what ChatGPT and other things can do, like the patient comes into the office and has a problem, then a neural net or an artificial intelligence might eventually find out what he has, right? So it can help the physician. I think even now, the only thing is, I mean, in Germany it's a big thing, we don't have the data, because nobody allows to take the patient data into a big bank to sort of search it and make it. I don't know how it's here in Poland, but in Germany it's impossible. So this allows not to use this tool, which could be extremely helpful. And we will see, I mean, I think in Denmark, Sweden, they are running around a different route. They allow more than we do in Germany. So what happens, whether they will sort of be ahead of us at a certain stage or not. But otherwise, I mean, if it's a model which has some physics behind it, one has to think still to get the best neural network. Because the training is very
Sometimes
expensive.
we can, for instance, design the special materials, composite materials, and then having this multi-scale method, we can simply try to estimate what should be the ingredients of this material. Really.
Yeah, people do that. I think, I mean, maybe you are a specialist, but I have seen that actually being on the review panel this year on the ERC for the consolidator grant. There was especially a grant on this topic, which actually wanted to investigate 1 million different microstructures and put it all together and use it for the design of better materials.
Usually engineering.
Questions? Yes, please.
Well, first of all, let me thank you for the excellent lecture, as always. I enjoyed very much your talk. There are many things that you talked about, but one thing struck me a little bit. You said when modeling the sand, we are not in a position to model every grain using the discrete element method. Don't you really think that in near future, it may be still possible to model the soil particle by particle?
No.
With the new computers.
Of course, with the development of computers.
No. Actually, to be frank, I don't. Well, I mean, I don't think we stopped at 300 million. So that was sort of the one we could somehow handle. That was quite a big system already. My feeling is that you need something like a multi-scale type of thing. I mean, we had some work on that. That's interesting. You do the sand with particles, and outside you do a continuum model.
Homogenization.
So then, by this, you can basically sort of model correctly, but you have to be careful that the continuum model has the same constitutive behavior like the send, but if you manage to do that, then this is, I think, the solution, and this will be in the near future possible. But the only thing is you have to have some codes who can cover this.
Thank you.
Okay, so I see no more questions. So, Professor, thank you very much one more time.
Yeah, thank you.
So, thank you very much, the audience, and see you next time during next lesson. Or lecture, so.
This lecture
Was
is
it
like a
also
lesson.
lesson?
Yes.